start by giving you one example. So implicit differentiation. Well, there is this example for you. Example 1 says, find the derivative of this function y equals to x squared plus 1. The second example says, now find the derivative of y squared equals to x squared plus 1. The third example says, find the derivative of, let's take a look at this, y squared equals to x squared times y plus 1. How do we find the derivative of these maps here? Well, the first one is not very hard. We already know we have a quadratic expression and we can take the derivative easily. Y prime is equal to, well, the derivative of x squared is 2x and the derivative of constant is 0. So you can quickly write down y prime or dy dx is equal to 2x. So, or dy over dx, the rate of change of y with respect to x is 2x. That makes sense. But what should I do about these two cases here? You have two options. The first option is applying implicit differentiation. How does it work? We start taking the derivatives with respect to x from both sides. The derivative of y squared is 2y dy. So this is 2y, and we need to add the elements of taking the derivative of this function. Whatever this function is, we need to have dy as well. On the right-hand side, we take the derivative with respect to x, 2x dx. So I'm going to use a different color so you can differentiate between these. Dx. Now, the derivative of the constant is just 0, so we're just going to ignore that. Very well. So what's next? Okay, you have 2 on the left, 2 on the right. You can easily cancel out these two numbers, get rid of them. Then divide both sides by dx and also y. Divide by dx. What is our goal? Our goal is to create dy over dx. So if you divide both sides by dx, you can get rid of dx from right hand side and you are creating dy over dx. So it's going to be y dy over dx equals to x. Now what? I need to isolate dy over dx on one side. So by dividing everything by y, we can have that isolated on one side. Divided by y, divided by y. So dy over dx, or the derivative, is equal to x over y. Very well. How about this guy here? Okay, so first of all, note that we are taking the derivative of y squared with respect to y. So what do we have? Let me write it down here. I need a little bit of more space. X squared y plus 1. The derivative of y squared with respect to y is 2y. But since we are taking the derivative with respect to y, we need to have dy equals to. Well, now you have to stop. Here you have multiplication. It means that you have to apply product rule. Product rule. Okay. Product rule. So first take the derivative with respect to x, which is 2xy dx. So this part is the derivative of with respect to x. Plus, now take the derivative with respect to y. It means that you're left with x squared dy. This is the derivative with respect to y. And the derivative of the constant is just 0. So what do we have? We have 2y dy equals to 2xy dx plus x squared dy. Remember that your job is to create dy over dx. This is equal to the derivative of the function. Divide everything by dx. Divide by dx, divide by dx, divide by dx. So what do we have? We have 2y y prime equals to 2xy plus x squared y prime. You need to have all of the derivatives on one side. So subtract x squared y prime. We get 2y y prime minus x squared y prime equals to 2xy. Factor out y prime. So let me see, do you see the board? Yes. Factor out y prime. 2y minus x squared equals to 2xy. What's the meaning of that? It means that your derivative is equal to 2xy divided by 2y minus x squared. Well, give us another example. Of course. So here we have this crazy looking combination of x and y. Suppose you have a surface in the space and you're interested in having a formula for the rate of change of that surface at any given position. Well, the surface is given to us as